Hi, folks. Why don't you let me know in the chat if you can see the slides, see me. Excellent. I've got some audio lag here, so I'm going to change those settings.
All right, so now let me ask again whether you can hear me as well as you could hear me a couple seconds ago. Oh, better. Good. Was the audio not synced up with the video? I was trying to use my AirPods, which otherwise are the greatest invention ever, but maybe they don't work well for the live streaming. Well, I'm glad you're all here. What I'd like you to do is post in the chat there where you're watching this from. Whenever I've done this in the past, at least one student has gone to the lecture room and streamed the video while sitting in our lecture room. And at least one student has been watching from a different state. Some students have watched from their childhood bed. So I'd like to know where you're watching from. And as you can see there on the front slide, feel free to post in the live chat. Or if you want to ask an anonymous question, feel free to send text to my Google Voice number, as you may have done in the past. All right. So we've got some Wisconsin, we've got some Wilson and Walter Library, Memorial Union, Udolph. Unhappy Wisconsin? Why unhappy? Oh, maybe that's because of the joke I made when we were talking about the topology of the real numbers. Lind, living room, nice. Bed at home, nice. Check, I've got that one. Is anyone watching from a state that's not adjacent to Minnesota? Tennessee, there it is. Shakopee, Lakeville, Woodbury, excellent. These are all places I visited, usually in my role as a baseball umpire. So that's great. Glad you're all here. For the next 10 minutes or so, I'm happy to do sort of a mini office hour. If you have questions that are on your mind, feel free to put them in chat there. Or, like I say, send me a text to my Google Voice number. And then I'll start for real here at 11:15. What part of Chicago, Amelia? I went to graduate school in Chicago, met my wife in Chicago. She grew up in Evanston. My PhD is from the University of Illinois at Chicago. She was at Northwestern at the time. So I know Chicago well. Spent 3 years of my life there. In a Starbucks in Roscoe Village. Nice. I've been to cafes in Roscoe Village myself. I'm not sure Starbucks had invaded Chicago yet when I was there in 1995, but it was getting close. Of course, this happens every time I live stream from home. You can see that I'm at home here. I'm in St. Paul, Minnesota. And of course, there's some kind of pile driver outside our house. I don't know if you can hear that, but it's probably not loud enough to be distracting. So if you're just coming in, I'm asking people to let me know where you're viewing from.
Just coming in.
And so people are having trouble with the audio now. So keep me posted on whether that's working. I'll make sure that my audio settings are right here. And as I mentioned before, I'll start class for real at 11:15. In the meantime, feel free to... Okay, you can hear me fine. You can't hear the heavy machinery outside my house here in St. Paul, Minnesota, near the campus of Macalester College. All right, that's a relief. You can hear me, but not the pile driver. So I got asked a question by text, and thanks for that question. The question was about Cauchy sequences and their accumulation points. Let me just write this down. So you remember that we proved in class that sequences are Cauchy if and only if they're convergent. And so that's something we've proven. And you may remember that the Cauchy criterion turned out to be a useful tool for us to show that a sequence is divergent by showing that it's not Cauchy. And in principle, we would be able to show that a sequence is convergent by showing that it's Cauchy without knowing in advance what the limit is. And the question was about accumulation points, which we'll talk about a little bit here during our lecture today. And keep in mind here that Cauchy and convergent are adjectives or properties that apply to sequences, whereas sets have accumulation points. And so it is true that you can consider sequences to be the set of points in the range of that function. So consider the range of that sequence as a function, and then you can ask whether that set has an accumulation point or not. And as the asker implied in her or his question, it is true that if a sequence is Cauchy, then that range set will only have one accumulation point, and that accumulation point has to be the limit of the sequence. And so we'll investigate. Pardon me. We'll investigate this relationship between a sequence's limit, if it's convergent, and the corresponding set's accumulation points. What we'll talk about is an example where we have a sequence that's wildly divergent, but yet it has a set of images where every real number is an accumulation point, and hence we'll be able to find a subsequence converging to every real number. So that's sort of a nice foreshadowing for some of the ideas we'll talk about today. So I see that Mary there asked about the practice midterms. I posted sample exams for exam 3 yesterday. And once we get started here at 11:15, I'll talk a little bit about smart use of those practice tools here in the next week and a day. So I'll get to that here in about 2 minutes. And I'll go back to the main page here. And as always, feel free to let me know in the live chat there or by text if there's something that you're not seeing well, or if you start not hearing me well. Though I expect, if anything, you might be able to read the slides here a good bit more easily than you can in the lecture room. So let me know if that's not the case. One final request here for 411. Let me know where you're watching from. Any far-flung states or countries, I would enjoy hearing about that. Maybe if you're still on campus, it's because you have other class meetings today that are not virtual. I see that more than a couple people are watching from Walter Library or Wilson Library. Is anyone watching in the presence of another student in the class? Excellent. You are watching from a bar in Nashville, Tennessee. Let's see, it's 12:14 p.m. I think in Nashville. I think it's Eastern time in Nashville. So I won't ask what your beverage of choice is here during Math 3283W. But glad you're here, whether it's from a bar in Nashville or from Walter Library or from the bed in the house you grew up in. Is anyone watching within earshot of a family member? So my son is in the next room over. He may pop in. I doubt it, but he may pop in sometime here. All right, so let's get started. Glad you're all here. we'll go from now 11:15 until about 12:05, and I'm happy to stay after for about 10 minutes after if you have follow-up questions. Today we're going to talk about subsequences again, section 4.4, and some content from 8.1 on infinite series, which you're familiar with from Calculus 2. Let me give you some details about the exam and preparing for that. Our third exam will be next Thursday, November 29th. It will cover section 3.4. Remember, that's the section on the topology of the real numbers. Section 3.5, that's on compact sets, and I have an asterisk next to that section because I'm asking you to know only one thing from that section, and that's the statement of the Bolzano-Weierstrass theorem, which is that bounded infinite sets must have an accumulation point, and in fact we'll use that statement today. And as I think I mentioned in class before, much like the completeness axiom, I can 100% guarantee you that I will ask you to state the Bolzano-Weierstrass theorem on the exam next Thursday. So chapter 4 there is about sequences, the chapter we're wrapping up today. And then section 8.1 we'll talk about today and next Monday. Next Wednesday we'll spend all the time you like reviewing for that exam. And then I'm writing there not section 8.2 because I think maybe last week I left open the possibility that we will have covered 8.2 by the exam. Let's not push it. So 8.1 will be the last section. And then needless to say, chapters 5, 6, and 7, we won't be covering in much detail at all, and certainly not right now. Those chapters would be the basis for a course like Math 4603. So there are some exercises to practice for exam 3. I'll mention here that sometime toward the end of our session here today, I'll give you information about redeeming those 3 bonus points for your quiz score. So as I said before, feel free to post comments or clarifying questions either there in the live stream or by texting my Google Voice number. Okay, so let's remember what we've done. On Monday we defined what a subsequence was, and it comes from an increasing function of natural numbers. N1 less than N2 less than N3 and so on. And as I encouraged you to view this on Monday, think of it as making a choice of elements of your subsequence from the original sequence, but you have to make the choices in such a way that the indices are always increasing. So I don't know if you remember this famous clip from the show I Love Lucy, but Lucille Ball is there at a conveyor belt of cookies or candy, and some of them she grabs and some of them she doesn't, but because the conveyor belt is moving, the third one she chooses will be further along in the original sequence of confections than the second one she chose. So that's what that string of inequalities means. So on Monday, we proved that if a sequence converges, and if its limit is a, then every subsequence of that sequence also converges to that number. And so we use that theorem as a tool in a couple different ways. Remember, we showed that certain sequences diverge by showing that they have subsequences that converge to different numbers, in which case the original sequence must diverge. And we also used the theorem as a tool to find the limit of convergent sequences by using the subsequences to set up an algebraic relationship involving the limit of the sequence. So that's what we did on Monday. And so now let's talk about subsequential limits. And I like to think of this as a sort of tool for investigating how badly sequences diverge. So we'll say that a number a, is a subsequential limit of a sequence if it's the limit of some subsequence of that sequence. And so let's write down some examples here. So let's think about how badly sequences can diverge. How many different subsequence limits can a sequence have? So let's give an example of sequences that have no subsequence limits, 1, 2, 3, and so on. All right, so we're well familiar with the example a sub n equals n. And we've seen that not only does that diverge, but it diverges to positive infinity. And furthermore, it doesn't have any subsequences that converge. So that divergent sequence has no subsequential limits. What about sequences that have one subsequential limit? Well, it's true that every convergent sequence if it has limit a, then we proved on Monday that every subsequence of that sequence must also converge to a. And so every convergent sequence has exactly one subsequential limit by that theorem. But you might have the impression that if a sequence has one subsequential limit, then it must be convergent. But that's not true. Imagine a sequence that operates like this. Imagine 1, 1/2, 3, 1/4, 5, 1/6, 7, and so on. And so what you can see is that the odd index terms are growing like n, and the even index terms are acting like 1 over n. And so this sequence diverges. It doesn't diverge to positive infinity because it's always having terms of the sequence hop back to 0, but it does have a subsequence that converges to 0. And so this has one subsequential limit, zero, but doesn't converge to 0, but it diverges. All right. And so now notice that as soon as we have more than one subsequential limit, the sequences we're talking about have to diverge, all right? Because the theorem prohibits convergent sequences from having more than one subsequential limit. So for example, an alternating sequence like 0, 1, 0, 1, and so on, that has two subsequential limits, 0 and 1. And for that matter, you could imagine a sequence with 3 or 4 or any finite number of subsequential limits. So 1, 2, 3, 1, 2, 3, and so on. All right. But there are sequences that can diverge much more chaotically than that. And so in order to think about that possibility, we have to return to some of our work on cardinality from chapter 2. So let's look at an example, and I use the word example loosely here because it's not going to be constructive. But let's think about how a sequence could have a subsequence converging to every real number. And then because that's going to be ultimately kind of unsatisfying because it's not concrete, we'll look at a similar and concrete example of a subsequence converging to every real number in the closed interval 0 to 1. Sure, so Ankita had asked about the sequence 0, 1, 0, 1, and so on. That has two subsequential limits, 0 and 1. And so, oh, did I write something wrong here? Right, okay, and C, that has two subsequential limits, 0 and 1. And that comes from the fact that, for example, the odd index terms are the constant sequence of zeros converging to 0, and the even indexed terms is a subsequence that's constant converging to 1. All right, so let's think about a sequence that has a subsequence converging to every real number. And so what this relies on is the fact that the rational numbers are countable. In other words, there is a bijection from the natural numbers to the entire set of rational numbers. So there's a bijection, let's call it A suggestively, from N to Q. All right, and I'm calling it A because this bijection determines a sequence, and the sequence is just A of 1, which we call A sub 1, A of 2, and we're calling that the second term of the sequence, and so on. All right, and so we gave part of the proof that the rational numbers are countable by writing down, you might remember, a function that maps rational numbers to numbers of the form 2 to the m times 3 to the n, where the input was m over n. In any case, if we have such a bijection, then let's show that we can construct a subsequence of this sequence A sub n that converges to any given real number x. So let's show that this sequence that comes from this bijection, show that this sequence has a subsequence converging to any real number x. All right, so let's let x be a given real number. All right, and then the important observation to make here is that if we look at the neighborhood around x of any radius epsilon, because the rational numbers are dense in the real numbers, since the rational numbers are dense in the set of real numbers. And now remember what that means. All dense means is that between any two real numbers, we can find a rational number in between there. And that was a consequence of the Archimedean property that we studied in chapter 3. All right, but what that means here is that inside every neighborhood of any radius of this given real number x, it contains not only one rational number, but infinitely many rational numbers. And it'll be important for us to have that infinite fact here. Infinitely many rational numbers. And because it's a bijection, it'll contain infinitely many A sub n's. All right? Every rational number corresponds to some A sub n. And the reason that it contains infinitely many A sub n's is that if there were only finitely many, then we could choose epsilon to be the smallest distance from x to those finitely many A sub n's. And then that neighborhood would have to miss the rationals completely. But that can't be true because the rational numbers are dense in the real numbers. So this neighborhood contains infinitely many rational numbers, contains infinitely many members of this sequence that lists all of the rational numbers. So I'm going to pause here. I see Kyle's question about epsilon. Yes, epsilon is arbitrary here for every epsilon, but in our proof that comes soon, we're going to be specifying radii, 1 over n. And then when we ultimately prove that our subsequence converges to x, then yes, we will let epsilon greater than 0 be given. Okay, so first we're going to construct a subsequence, and then we're going to prove that it converges to x, starting with the sentence that you wrote. And while I'm pausing here, I'm going to check text here. Yeah, so later on in this hour, I'm going to tell everybody how to get that quiz bonus. So that's coming up. All right. So then here's how we construct it. All right, let's choose an A sub n sub 1 that belongs to the neighborhood around x of radius 1. We can choose that however we want. All right, and then our plan is that for each k, I'm using k as the input, so to speak, of our subsequence, thinking of a subsequence as the composition of two functions, one of which takes k to n's, and then the original sequence takes n's to a sub n's. And those are the rational numbers that are listed in this bijection. So for each k, we're going to choose an a sub n sub k in the neighborhood of x of radius 1 over k. All right? So in other words, we're going to be choosing a sub n sub k's in such a way that they're getting closer to x. But the potential problem is that we have to make sure that the indices we choose satisfy the subsequence requirement. In other words, the indices have to keep going up. And so that's why we need the infinitely many property. Because what we're going to do is construct our subsequence inductively in the following way. Having chosen a sub n sub k, we're going to choose a sub n sub k plus 1 in such a way that it belongs to the neighborhood of x of radius 1 over k plus 1, so they're getting closer to x, and we want to make sure that n sub k plus 1 is bigger than n sub k. And so you ask, well, how do we know that there is an n sub k plus 1 that's bigger than the n sub k that we already chose? Well, it's because there are infinitely many rational numbers to choose from. And if there's infinitely many, then there has to be one with an index that's further along down the conveyor belt than n sub k was. So it's this observation up here that allows us to make that choice. All right? And so by induction, you see what we've done here is chosen an a sub n sub 1 that allows us to choose an a sub n sub 2, and so on. And so, having our subsequence now, a sub n sub k, let's show that this subsequence converges to x. And x is a arbitrarily chosen random number, okay? And so now here, Kyle, is the place where our proof will start. Let epsilon greater than 0 be given. All right? And so because each a sub n sub k is within 1 over k of x, all we have to do is choose k large enough so that a sub n sub k will be within 1 over k distance of x. And so our choice of capital N will be such that 1 over capital N is less than epsilon. So then if k is bigger than capital N, k being the input of the subsequence function, then 1 over k is less than 1 over capital N, and that's less than epsilon by choice. And now notice how we get the inequality that we need that shows a sub n sub k is getting close to x. And if k is bigger than capital N, then a sub n sub k minus x is less than 1 over k. And that is true since we chose a sub n sub k in such a way that it's in the neighborhood around x of radius 1 over k. So that inequality is true. And 1 over k is smaller than 1 over capital N, which is in turn smaller than epsilon. So that shows that we can construct a subsequence that converges to any real number that we want. Now, granted, that's a little unsatisfying because we can't really list all of the rational numbers. We just have to accept our theorem from chapter 2 that there is a list of all the rational numbers. And so that's why I think it's a good idea to give a more concrete example here. Let's write down a sequence of rational numbers that is a bijection with the rational numbers from 0 to 1. All right, so let me write, here is a bijection A from the natural numbers to the rational numbers that are between 0 and 1 inclusive. All right, so so here's the construction. Let's start with 0 and 1. And now every rational number between 0 and 1 can be written as a fraction of whole numbers where the numerator is less than or equal to the whole number in the denominator. And so the plan will be to list all of the rational numbers with denominator 2 in lowest terms that haven't been listed already, then list all the rational numbers with denominator 3 that haven't been listed already, and so on. All right? So I'll list these and then get to a couple of your questions. So we list 1/2, and then we list all of the rational numbers between 0 and 1 that have denominator 3 in lowest terms that haven't been listed yet. And then we list all of the rational numbers between 0 and 1 with denominator 4 in lowest terms that haven't been listed yet. 2 over 4 has already been listed, so we post 1/4 and 3/4. And then we post 1 over 5, 2 over 5, 3 over 5, 4 over 5. And I won't do this for very long, but I will do the ones with denominator 6. We get 1 over 6, 2 over 6 has already been listed, 3 over 6 has already been listed, 4 over 6 has already been listed, and 5 over 6, and so on. That hits every rational number between 0 and 1 inclusive. And so we would be able to make a similar argument about this sequence that we did for the sequence in example 1. Now let me scoot back here and address Tala's question on the previous slide here. Tala's asking about this choice here and asking whether it's part of the proof. It is part of the proof that there is a subsequence that converges to X. And so from here to here, what we've done is constructed a particular sequence, knowing that we have that original sequence given by the bijection. And then the second part, the language of which Kyle was asking about, from here to here, that's our proof that the sequence that we constructed does indeed converge to X. And what we showed was that the reason it converges to X is because we chose our subsequential members to be getting closer and closer to X because they're in those 1 over K neighborhoods. Okay? So let's see, Meredith had asked about where do the rational numbers come in if it says real numbers in the statement. So let me scoot back here and say that we're picking an arbitrary real number X here, but the reason we're dealing with A sub n sub k's that are rational numbers is because our sequence comes from this bijection that has domain natural numbers and range rational numbers. So we can't write it down explicitly, but knowing that we have such a bijection is equivalent to writing down a sequence of rational numbers. That's where the rational numbers are coming in. And yes, as Nick said, we're using the fact that the rational numbers are dense in the real numbers when we make our choices of rational numbers that are in neighborhoods that are as small as we like. And yes, absolutely. So Mary's got it exactly right. When we choose A sub n sub 1 in the neighborhood around X of radius 1 divided by 1, so to speak, that's like that choice is our base case in a proof by induction that we can make such a construction. Okay, great. You all are asking questions that really get at the heart of what's going on here, so I appreciate that. All right. And so, as a way of investigating how badly sequences diverge, let's talk about lim_sup and lim_inf. But because it's 10 to 12 here, I want to make sure that you get the information about that quiz bonus. I know you're all here for the mathematics, but the 3 points can't hurt either. So let me find that. Okay, so here's the plan. By by 12:15 p.m. today, let's say, what I'd like you to do is send me an email from your UMN email address to my UMN email address, mosher@umn.edu. Put in the subject line the word present, as in I am present today. It doesn't have to have anything else in the body of the email, and I'll use that to filter those emails and make sure that you get credit on Moodle for 3 points to your final quiz score. Remember, that's calculated via best 7 of 9 quizzes out of 20 points each, so that'll be a 140-point quiz score. And those plus 3 count up to the maximum of 140. All right, so that's the plan. Make sure you do that right after class or now if you're taking off, but by 12:15 today. All right, let's talk about limb soup. All right, this is like peanut butter and chocolate. Two concepts, mathematical concepts that go together to make a limb soup here. Let's deal with bounded sequence. Let's go with bounded sequences for now. And then let's let A be the set of subsequential limits of this sequence. Let's define the limb soup of this sequence to be the supremum of that set of subsequential limits. All right, so remember those inequalities that define what supremum is. There's an inequality that says that this number is an upper bound for that set of subsequential limits, and it also says that any smaller number will not be an upper bound for that set. If the sequence is bounded, then the set of subsequential limits will also be bounded. And we'll be able to show, I think I'm going to save it for Monday, that bounded sequences have to have a convergent subsequence. And so then we'll know that the set is non-empty, and hence the supremum of that set has to exist. Why? By the completeness axiom. The completeness axiom says that in the set of real numbers, non-empty sets that are bounded above have a supremum. And so this concept, limb soup, is well defined for bounded sequences. So that's the theorem that we'll save to Monday. Every bounded sequence has a convergent subsequence. And then let's write down some subsequential limits here. Let me just glance in at the questions here. Let's see. So, is it that slide that you wanted to see, Tala? We're defining the limb soup of a sequence to be the supremum of the set of subsequential limits. And so now let's work a particular example. Okay. So let's define a sub n to be the cosine of n pi over 2. And so a sub 1, I'll draw in black here, not pink. A sub 1 is 0. A sub 2 is negative 1. A sub 3, we're cycling through the unit circle here. A sub 3 is 0. A sub 4 is cosine of 2 pi, which is 1. And so you can see that all of the odd indexed terms are 0. All of the terms where the index is a multiple of 4 are 1, and all of the terms of the form 4n minus 2 are negative 1. And so let's just get comfortable with the notation here. The set of subsequential limits is negative 1, 0, and 1. All right, so let's be clear here. Negative 1 is in that set because there is a constant subsequence converging to negative 1, and same is true for 0 and 1. And so then what that means is that the lim sup of this sequence is 1. All right, we're just finding the sup of this sequence. Okay, and then the lim inf, the limit inferior, or the infimum of the set of subsequential limits of the sequence, is equal to negative 1. All right. And so let's talk a little bit about a characterization of lim sup that looks kind of like our definition of convergence, but certainly this concept allows for the possibility that a sequence does not converge. Okay? So if we have a bounded sequence, then when we prove that theorem, we'll know that we have a lim sup. And here's what it means for M to be the limit superior of a sequence. These conditions are on the next page here. M is the lim sup if and only if, for every epsilon, there exists a capital N such that if n is bigger than that capital N, maybe it's good to say for every n bigger than that capital N, then A sub n is less than m plus epsilon. So, in other words, right here, what we're saying is that eventually all the terms of the sequence have to be below m plus epsilon. And another way to say that is that only finitely many of the terms can be above m plus epsilon. And so let's think about why that's true. If there were infinitely many terms of the sequence above m plus epsilon, but the sequence was still bounded above, then there would have to be a subsequence between m plus epsilon and whatever the upper bound of the sequence is that converges. And then m would not be an upper bound for that set of subsequential limits. And so that's the red condition that I've underlined here. Eventually, all the terms of the sequence have to be less than m plus epsilon for every epsilon. And the second condition is that for every epsilon and every capital N prime, we can find another n bigger than that capital N prime, such that A sub n is greater than m minus epsilon. And so the green condition here is saying that there have to be infinitely many terms of the sequence above m minus epsilon. And let's think about why that's true. If there were only finitely many terms of the sequence greater than m minus epsilon, then m minus epsilon would be a smaller upper bound for all of the subsequential limits. There couldn't be any limits of subsequences between m and m minus epsilon. So that would mean m is not a supremum for those subsequential limits. So those two properties characterize what lim sup means. And I think it would be useful to go back and think about sort of an instructive example. So this is a sequence we're well familiar with. 1 over n converges to 0, and as it's true for any convergent sequence, the set of subsequential limits has just one number in it, 0. And so the lim sup of that sequence is 0. But notice importantly here that m is the least upper bound, the supremum, for the set of subsequential limits, but it's not an upper bound for the entire image of the sequence. All right? And so to reproduce, so to speak, the picture on the previous page, if this is 0 and this is our epsilon, and here are the terms 1, 1/2, 1/3. Whoa, can't go past 0. Here are the 1 over n's. Playing capture the flag with 0 or with epsilon there. All right, those are the terms 1 over n. Notice what we're saying here is not that 0 is an upper bound for the entire sequence, but in terms of that characterization on the other page, no matter where we put epsilon, there's only finitely many terms of the sequence to the right of that. Okay? And that'll be true even for divergent sequences. So Andrew asks there, can you have a sequence where the lim sup equals the lim inf, but the sequence doesn't converge? No, in fact, if you use this characterization, you would be able to show that such a sequence actually has to converge. So what you might like to do is write the corresponding characterization for lim inf and then kind of put them together Frankenstein style to construct an argument that the sequence actually has to converge to that common number. All right, so I just want to take 1 minute here to give a sense of why we should even care about lim sup. The reason that we're caring about lim sup here is that we'll be able to state a more general ratio test for series with it. So let's try to remember what the ratio test told us in Calculus 2. So you might remember that the ratio test goes something like this. If the sequence of ratios a sub n plus 1 divided by a sub n converges to a number L that is less than 1, then the infinite series of terms a sub n converges absolutely. And you might remember that what we mean by absolute convergence is that not only does that series converge, but the series where the terms are the absolute values of all the terms also converges. And so what I want to end with here is that we'll be able to prove an even more general version of the ratio test in the following sense. This sequence of ratios, it might diverge. And if it were to diverge, then in Calculus 2, we wouldn't be able to do anything more about it. We wouldn't be able to use our favorite tool, the ratio test. But we'll prove that so long as the limb sup of this potentially divergent series of ratios is still less than 1, then the ratio test works just as well. And on the other hand, you might remember that if that L, that limit, is greater than 1, then the series diverges. That still requires the sequence of ratios to converge. But even if it doesn't converge, and we can show that the lim inf is greater than 1, then we'll still be able to use the ratio test that we knew from Calculus 2. All right, so our plan for Monday will be to go back and prove that bounded sequences have to have convergent subsequences, and that proof will be very much like the techniques that we developed for that crazy sequence converging in subsequence to every real number. And then we'll work some examples that, frankly, you're probably familiar with already from Calculus 2. So we'll wrap up our content from Fort 4 and 8.1 on Monday. We'll do whatever review you like on Wednesday, and then the test, as I described at the beginning, will be on Thursday of next week. I want to point out that if you're looking for practice problems from section 3.4, then check my note on the Moodle site about where to look in exam 2 samples for problems from that section. And then you'll also see that there will be some problems in the exam 3 samples that can be ignored for your preparation for exam 3. Okay, so let me just glance through the questions that have been posted here. As I mentioned, I'll stick around here for 5 or 10 more minutes. Glad you all tuned in, and I hope that you have a nice holiday with family, friends, and loved ones, and I'll see you all on Monday morning. So let's see. Yeah, this is a good observation that Tala is making. If a sequence is increasing, then there will always be no elements to the right of the limb sup. In fact, if a sequence is increasing and it's already bounded, as we're assuming if we're talking about limb sup, then we're exactly in the situation for the monotone convergence theorem. And so in that case, not only does the limb sup behave that way, but the limb sup is actually the limit of the sequence, which is convergent. All right, so it looks like Jackson is giving everybody bad advice. So feel free to like and subscribe, but that's not going to earn you the extra credit quiz points. I'll follow up with Jackson about that post, but that's not how you get the extra credit quiz points. I described how you do that earlier in the discussion, and I'll be asking you to do that by 12:15. All right. Thank you for the kind wishes. I hope you all have a happy Thanksgiving as well. I'll stick around here for a couple minutes if people have other questions. So I'll go back to that slide since there was a question about the time. 12:15 Central Time. That's the deadline. And somebody had asked in the text whether you have to specify 3283W. No. There doesn't have to be any text body, just a subject line that says present. And then I'll filter them, alphabetize them by email address, and then enter them into Moodle so that you can check that you got the credit. Nick is asking, can we define any function from n to n to describe the terms of the sequence we would like to choose for the subsequence? Given that k is greater than 0, we choose k squared. So you get the 1st, 4th, 9th, 16th terms of the sequence. Yes, absolutely, that's a fine way to specify a subsequence. But the critical observation here, Nick, is that I'm going to write it right here on this page. So the function in question here is n of k equals k squared. And the important thing here is that k squared is an increasing function. And so, in other words, n sub 1 is less than n sub 2, which is 4, is less than n sub 3, which is 9, and so on. So yes, the function you wrote down, k squared, satisfies that index requirement, that the indices are going up. So I don't know if Nick is still around, but I hope that gets you what you needed there. All right, so I don't know who Klepto is, but it looks like you got what you needed there. Excellent. All right, Nick. Okay, so I am going to sign off now, and I'll look forward to seeing you all in person on Monday. Sometimes students ask, why don't we just do this all the time? And I have to admit, I think it does go pretty smoothly, but on the other hand, I like the ability to sort of interact in real time with your comments and your questions. So I'll look forward to getting back to that on Monday. All right, folks, have a good holiday, and I'll see you then. Bye.